Hi everyone, so we are going to do some practice FE exam problems for probability and statistics. So let's go ahead and get at it. How many different 5-card hands can be dealt from a deck of 52 cards? So different kind of indicates distinct. So we're going to do permutations, not combinations. So it'll just be kind of this function n minus r. So our total number of things that we can have is 52 for our cards. We're going to select from that r equals 5. So 52 minus 5, that's going to be 47. So this one right here. Excellent. So again, remember, permutations are distinct. Combinations are not distinct. So let's go to our next one. A lottery draw consists of picking balls number 1 through 60 from a rotating drum. What is the probability of drawing the 20 ball or an odd numbered ball during the first draw? So this is basically we're going to do probability of A or basically B. So we're going to be, where's the union? So if they are not mutually exclusive, we will just add the probabilities of A and B. If they are mutually exclusive, we're going to have to add the basically minus A and B occurring. So probability of drawing 20 or an odd, so that's fine. So probability of 20, our A event, is going to be 1 over 60. An odd number, because 20 is not odd, that is just going to be a half. So we're going to get 31 over 60. So be careful of if they're mutually exclusive or not mutually exclusive events. So we have to make sure, be very, very, very cautious about that. So let's do another one about independent events now. So if a baseball player has a probability of 0.25 for hitting a pitch ball, what is the probability that the player will miss? So the probability to miss is just going to be 1 minus 0.25. Which is equal to 0.75. What's the probability that miss 3 pitches in a row? So 1, 2, and 3. So this is where we're actually multiplying because there's 3 events. So 0.75 times 0.75 times 0.75. So 0.75 cubed. That will give us something once the Mathematica wakes up. We're just waiting for it. About 0.42. There we go. So let's go on to the next one. So we're looking at our normal distribution. These are the results. I just knocked my coffee. If an AIT exam indicated a mean score of 68, standard deviation of 14, assuming a normal distribution, what percent of the people scored above 95? So you can do this multiple ways. If you have a calculator like this, you can do PDF equals 1 divided by square root of 2 pi times exponential minus z squared over 2. And we can integrate this. So we need to see our z value here. So our z function is going to be our measurand, x, our mu, and our sig. And our z value is going to be x minus mu divided by sig. Our z function here is, we're saying 95, the mean is 68, sigma is 14. So we look at this value here, 1.92. So I could integrate my PDF, because we're looking for what percent of the people scored above 95. So we're going to integrate from z, from that value of our measurand to infinity. And that will give us, so a little more than 2.5. We can look that up in our notes. A z of, what was our value? 1.28. So let's just say 1.93. So let's go to our notes here, our z table. 1.93. 1.93 is going to be 0.4732. And greater than will be 0.5 minus that. So that should give us approximately that value here. So we're going to say Again, it depends on kind of where you choose. So in our examples, can be a little bit more than 2.5% because we solved it exactly. So your answer can be off a little bit depending on if you're looking at a table or, excuse me, I'm going to say a little bit more there. Excellent. On to the next one. So we've got another normal distribution problem. So here we have 1,000 boards at a mean impedance of 100 ohms. QA indicates that 80% of the boards have an impedance between 95 and 105 ohms. The minimum acceptable impedance is 90 to 110. So how many boards are rejected per day? So one way we can figure this out is we know, for example, if I integrate my PDF from my z's function value of 95, the mean is 100, but we don't know what the standard deviation is. And then 105, 100, and x is 80% of our data set, so we can shift under that. That would be 3.9. Then we are also given, I'm going to paste that in here, that if now basically we're interested in how many, for example, what percent of our data is going to fall between these bounds. So 90 and 100, given what we solve for our mean here, 0.989. So, but we're looking at what exceeds this. So 98.9% of our data exceeds that. I'm going to do 1 minus. But then it's asking for, so that's the percent, but I'm asking for how many boards are rejected. So now I'm going to multiply that by 1,000. So around 10 will be rejected there. So we have a problem with a confidence interval of a mean. So during a routine physical exam, we sample n equals 100 of the 1,500 employees. We see a mean of 175 pounds and a sample standard deviation of 15 pounds. Basically, what is the 95% confidence interval? So this is large sample size. So we can simply we know that our z over 2 value, so if we do x bar plus or minus z over 2, which is basically z over 2 times f sub x over square root of n. So, and z over c over 2 is going to be 1.96. So I can do 175 plus 1.96 times, what's our standard deviation? 15 divided by square root of 100. Here we go here. So, and then we can do minus. Basically right here. Excellent. So that was kind of our good old problems that we're going to be doing very soon. Hopefully you're confident with that. No pun intended. All right. I have a deck of 52 cards, contains 3 jacks, 3 queens, and 3 kings. What is the probability either a king or a queen is drawn from a full deck? So, we're given essentially so we have 52 cards. King or queen, that's not mutually exclusive, so the probability that I draw a king is just going to be 3 divided by 52. Plus the probability I have to draw a queen, which is 3 over 52 in this kind of very strange example. So it's just going to be equal to 6 over 52. Excellent. Hopefully not that bad of a problem to solve there. All right. And you could actually, let's do 6 divided by 52. So you can actually give you a value to that. All right. So we have a bag contains 4 green socks, 2 blue socks, 5 red socks. 2 socks are removed. What is the probability the first sock is red? So let's do probability. So the first sock is red is what? I'm going to have 5 over how many socks? 4 plus, so 5 out of 11 times, once I remove that, the probability that the second one is green is going to be 4 out of 10. And then we can multiply that. So 5 divided by 11 times 4 divided by 10. That's that AND statement. It's about 18%, or 0.18. All right, let's move through here. All right. The annual rainfall in a city can be approximated as Gaussian. The mean is 15 inches. And we're getting our standard deviation cut off. Standard deviation is 2 inches. So let's go ahead and look. What is the probability that the rainfall in any year is between 18 and 20 inches? So we can do that. I can integrate my PDF from a value of z from my z function. We're looking at between 18, the mean is 15.2, and a z function of 20, 15, and 2. Let's look at that numerically. There we go, about 6%. And again, you can verify that using the tables as well. What's the probability that in any given year it's greater than 18 inches? So if it's greater than 18, 18 to infinity. Infinity. So here we go here. So there you can kind of see if it's greater than there, that's about, can be close to 7% there. Excellent. Let's go to the next one. A rare disease affects 1 in 1,000 adults. If a person has the disease, a test will show positive 99% of the time. If a person does not have the disease, the result will show positive 2% of the time. So basically a false positive. So for a randomly tested person, so basically we're looking at the probability that given they test positive, so a positive test, the probability that the individual has the disease, so B1 is going to be has disease, and B2 is going to be does not have the disease. So this is classic Bayes' theorem. So we're going to need to write this out as probability of B1, times probability of A given B1 over probability of B1 times probability of A times probability of A given B1 plus probability of B2 times probability of A given B2. So in this problem, probability of B1, so what is the probability that we have the disease? 1 in 1,000. So probability of B1 is 1 over 1,000. So the probability that we don't have the disease is going to be 999 over 1,000. What is the probability that we test positive given that we have the disease? So that'll be 99%, 0.99. Probability that we test positive given that we don't have the disease, that's going to be 0.02. So we can figure that out now. So we're going to be doing PB1 equals 1 divided by 1,000. PB2 equals 999 divided by 1,000. I'm going to say PAB1 equals 0.99. PAB2 equals 0.02. And we're going to be looking at probability of B1 times PAB1 divided by PB1 times PAB1 plus PB2 times PAB2. And it'll be like 4.7%. Hopefully it's there. Yep, there we go. We've got it. All right. So we have 4 fair dice. What is the probability of rolling at least 1 6? So one way you could approach this problem is actually from the opposite perspective. So what is the probability that we don't roll a 6? So it'd be 5 divided by 6 to the 4th power. And then 1 minus 5 divided by 6. Actually, let's just do 5 divided by 6 times 5 divided by 6. Let's copy this 4 more times. 4. And we can look at this. So we would get the following. So basically very close to 0.52. Excellent. So you can always take that opposite perspective as well. A bag contains 100 chips, numbered 1 to 100. One chip is drawn from the bag. What is the probability that the number on the chip selected will be odd or greater than 80? So these are mutually exclusive events, right? So we need to figure out, so first, probability that it's odd. That's going to be basically a half. Probability greater than 80. That is going to be basically 20% of the data set, so 1/5. Here we go. Now, what's the probability that we are odd and it is greater than 80? So what is going to be that one? Or that we have an outcome that is that. Let's think about it for a second. So probability that it's odd and we get a value that's greater than 80. So something that would satisfy effectively both of those values. So you can just do effectively, and we can actually break this down. How many of these would be? So basically you'd have, instead of a fifth, you would have to then look at half of that, right? So instead of 20 possibilities out of 100, it'd be 10 out of 100, right? So it'd just basically be, basically 1/10. So 1/2 plus 1/5 minus 1/10. There you go, which would be 0.6, which is right here. Excellent. All right, let's keep on moving. Final scores in a test are normally distributed with a mean of this, standard deviation of this. What is nearly the probability that a student's score will be between 65 and 78? So again, you see these popping up quite a bit. We need to know our normal distribution, z functions, all of those good stuff. So 65, we need a z function of 78. Our mean is 72, standard deviation of 10. 72, that's a typical bell curve. So we'll have about 48.37% right there. Great. Let's keep on rolling. 4 fair coins are tossed at once. What is the probability of obtaining 3 heads and 1 tail? So this is where you're going to have to basically look at some permutation values as well. But instead of this one, let's move on. Let's do some, we've done enough of these. Let's see. This is a decent, the average weight of most people start is 300 pounds. After 4 weeks, you take a sample of 28 individuals and find the mean to be 290 pounds, the standard deviation of 20 pounds. At 2.5 level significance, meaning we have, so remember, alpha is level significance, so it's 0.025. So basically, if we're looking at our confidence is equal 1 minus 0.025, which is equal to, our confidence level will be, what is it? 1 minus 0.025. I need a calculator. 1 minus 0.025, 97.5%. At this confidence level, can you determine if the individuals of this population have decreased in weight? So basically, we're asking ourselves the following question. Are we coming, is this sample, is this sample significantly different? So our initial hypothesis is our population mean is going to be equal to 300, our mu naught. That's our null hypothesis. Our alternative hypothesis is it is not equal to 300, i.e. statistically significant and different. So we can now or you can do a t-test comparison with this as well. But we can't really because we don't know how many samples we had initially. So Now we can do, what is our confidence level? 97.5%. And an alpha of 0.025.
Fully charged battery, fully charged.
That's my battery.
Unplugged charger.
It's fine. It is fully charged. It's fully charged. And it seems like, we're going to be doing actually that is going to be we're going to be doing a two-sided test here. So it's actually a confidence interval of 95%. So actually, we'll do 95. So now we have to figure out our t-value. So our t-value, theoretically, is going to be, actually we have we have x bar minus mu naught divided by r, minus mu naught divided by our standard deviation over square root of n. Why am I doing t? Because we're 28, that's small sample size. Our t alpha over 2 nu is going to be equal to t of alpha, which is, yeah, this question is very 0.025. Nu is going to be 27. We can look that up in a table, and then we can see if we exceed that value. Well, first let's find our t-value. So our x bar is going to be the 290 minus 300 divided by 20 divided by square root of 28. So if we look up we do two notes, look at our table. 4 here, all the way down. T of 0.25 of 27 is going to be this, so 2.473. But the question, actually, here we go. Actually, not that one. It's going to be 2.025. The question is, if that's our confidence interval, which is, again, it's poorly worded, so we are going to fall outside of that range. So in our confidence interval formalism, if we fall outside the range, we are going to reject H naught. So that is effectively what we'll be doing there. There we go. Let's go on to the next problem, because again, this value was less than that 2.05 value something. All right, let's go. Let's continue. These are just mean calculations, standard deviations. We've all done these before. Variance, sample size. Again, I think that we all know these ones. All right, how about this one? We've already done this one as well. Odd or greater than that. That was a good problem. Measurements of water, okay, are distributed with this and this. What is the probability of sample content above 16 or below? Ooh, this is a good. What is the probability that we'll have a sample taken, will have a water content above 16 or below 12%? So, again, it's the same normal distribution here, but this one's a little bit interesting because let's look at the first one. So it has a mean of 14.2, a standard deviation of 2.3, and we are now asked, what's the content above 16? So basically here to infinity, or, so this is that. And then below 12, so we'll do this. It's infinity. Excellent. So we can go ahead and see we've calculated those values here. So now, what is the question actually asking us? Well, we have effectively this. So basically, what is the probability a sample taken from the site will have water content above 16 or below that. So we can just basically add those probabilities together. Plus here, which will give us, yeah, about approximately this. Excellent. All right. Let's go ahead. Let's read some of the next problems. We're getting to the end here. What is the probability that exactly 2 heads or exactly 3 heads will be thrown if 6 fair coins are tossed at once? These are kind of combination problems. We've done these. I'm trying to look for some newer problems, things that we haven't really seen before. But these are all kind of similar. Let's see. Yeah, these are all, we're starting to reach the end of our time here together. But anyways, you're starting to see the pattern. So again, for your FE for probability and statistics, look at those mutual events, not mutual events, Bayes' theorem, some hypothesis testing, but a lot of these normal distribution and confidence intervals. So you should be well versed in that. So I hope this has been helpful, and I'll see you all next time. Thanks. Bye.